As we step through the individual instructions in our demo program, we observe the results of arithmetic instructions stored in the left-hand side operands, which can be register or memory locations such as EBX or value right here. The results are being updated, which is expected, and this is fine. But in addition to the target operands being updated, each arithmetic instruction also updates the flags, which are individual bits stored in register EFL. And this is called the flags register. We have seen the description of EFL bits in our prior presentation. So let's open it again. It was part of language components of MASM in the previous section. In this specific handout, we have a picture displaying individual bits inside this EFLAGS, also shown as EFL in our register window right here. So you see that some of those grayed out bits are not used and reserved for future, but some of these flags are used very heavily, and let's scroll down to the individual description of these bit flags. And if we want to examine individual flags such as carry flag or zero flag or sign flag or overflow flag, which are very important flags in our coding, we need to look at individual bits in the EFL value based on the bit position of these flags. So for instance, carry flag is the rightmost, the lowest position inside EFLAGS register. The zero flag is located at position number 6. Of course, positions are numbered from 0, so this is really the 7th bit of the EFL flag, and so forth. So to be able to examine individual flags, we will probably use some bit flag manipulation combined with masks for individual bits. For example, we can compute the masks that correspond to these bits inside the flag register by constructing this type of table. And in our experimentation, I'd like to take a look at the carry flag, which is located at bit 0, zero flag, which is at position 6, sign flag right here, which is at position 7, and the overflow flag, which is located at position number 11. Okay, so in order to produce the mask, I just need to take 2 and raise it to the power corresponding to the position of the bit. So we can take our calculator right here. Okay, so let's switch over to scientific, I think, format, and this is the power computation. So we can say that, of course, 0 raised to the 0 power equals 1. So this is, of course, value 1. Then if we continue with this, 2 raised to the 6th power, which is position of the 0 flag right here. So the mask for this bit, we take, again, we just clear and take 2 raised to the 6th power equals 64. Okay, so this is, I guess I'll just continue using decimal notation because this calculator automatic updates the result in decimal format, so I'll just write it here as 64. And then we also have the next is 2 raised to the 7th power, so it's like 64 times 2, so this will be 128. And finally 2 raised to the 11th power, so carry we just clear and raise 2 to the 11th power. Okay, so this gives us 2048. Okay, so we just align everything nicely. like this. And so this will be the values of our masks that we need to be able to apply to get to individual flags if we're using this environment, for this debugging environment, to analyze the values of our flags. So how can we, so these are our those are our decimal, and we can indicate that these are our masks, right? So these are the masks in decimal format. So if we then take an expression such as, for instance, this hexadecimal value, and I'll use C notation for the hexadecimal value, so this is the value of our flag, and apply the mask, which is bitwise AND in C, and apply masks such as 1, right, such as 1 right here, or 64 or 128 or 2048. These are the decimal values. We should be able to see the actual flag value. So to be able to do something like this, we can go to debug window, Windows, and we will open immediate window. Immediate window is like a calculator, which allows us to execute expressions like this. And I will use the question mark in front of it, so you see exactly what I'm typing in my immediate window. And if I take this, of course, this is the value taken directly from the register display. And if I just copy and paste this and hit enter, and you can see that it's set to 0, which indicates that carry flag is 0. Likewise, if I just use my up arrow key to bring it back and apply mask 64, which is the 6th bit set to 1 and all other bits are set to 0 in this mask, and apply it here. So it shows me that the 0 flag is set to 0. So let's try the sign flag, which is 128, like this, okay, also 0, and overflow flag, which is 2048, like this. You can see that it's also set to 0. So all of these flags currently, and I'll move this to the next tab group like this. You see that currently at this stage we're just about to return. I'm still running this program in debug mode, and we're just about to return from this program right here. At this stage, the flag register individual bits if we want to look at specific flags using these masks. So we can essentially get access to them and see the results. So the results here will be non-zero if the flag is set, and if the flag is cleared, we see 0 like we had it right now.